Day of academic adventures. Welcome back to Earth after yes, this party isn't after parties. Now we're going to do more serious things. We're having a keynote talk in this morning plenary session, and it is my pleasure to introduce our keynote speaker who will talk about a knowledge-based bioeconomy and the so-called green triple helix of biotechnology, synthetic biology, and ICT. The name of a person is Mr. Bob Maske, who is quite a distinguished personality. He's an executive working in the past in the academia, German Academy of Sciences, as a researcher, then a consultant, being a bridge between academia and industry, then moving to industry and growing up in his career in 25 years to that high as a vice president and fellow of one of the world's leading companies providing software tools in microelectronics and integrated circuits. So his professional experience is both in semiconductors and software development, which makes a wonderful mix, fully fitting the scope of our conference. So, a part of that, I'll say that the things Mr. Musk is doing right now is really cool stuff. He's trying to bring the rigid engineering design principles to the field, which was always famous for being messy and art-like without any rigid science in developing, to the biology, to natural sciences. So I'm really looking forward to listening how it may happen in the future, as biotechnology is well known as the top domain for the 21st century. Please, well, go ahead.
So first off, thank you to Baden for the nice introduction and the invitation to this conference. Also thank you to Alexander for this invitation to this conference. So as Baden pointed out, I'm going to talk about different subjects. The knowledge-based bioeconomy, and then the enabling technologies for this economy, namely biotechnology, synthetic biology, ICT. So my objective is actually to create awareness for these new trends. I keep the talk relatively general, as I don't know how much you already have in this. So let me give you a short overview. So this talk is going to be a little bit like a roller coaster ride, as we have to touch quite a different areas. So I'm going to start off with economics and engineering. Then we're going to add knowledge. Then we're going to add knowledge to. Okay, oh, that's better. Okay. So then we're going to add knowledge to these economic dimension, which leads us to the knowledge-based economy. We're going to add bio as an additional dimension. Now, if we want to talk about the next generation biotechnology, we need to talk a little bit about the principles of life, and then finally we're going to talk about the next thing after the next, which is synthetic biology. Now, in the course of doing so, we will also always touch a little bit ICT issues. Also, we'll introduce this qualitative thought model of triple helix. It's quite a useful model to analyze on a qualitative level the dynamics, the non-linear dynamics in complex systems. Okay, that's actually, slides are a little bit mixed up. So the first question is, I'm an engineer, why should I care about economics? The point being that normally economics is quite a distant concept to many people in research and industry who are working in research. Okay. So, don't think it's a boring concept. It's quite unusual. That's one start, as I said, with economics in a technical talk, but economics reality impact everyone's life on a daily basis. So if you think about the last financial meltdown, or if you think about your next round of negotiation, your project budget, it's all about economics. Another example which came up lately in the discussions here, where if you look for students who are willing to take an academic career, then again you won't find too much of them, because many of them decide to go to the industry. Again, a problem of economics. So in fact, economics is one of the most useful science, I guess, in practical terms, but unfortunately it's not well understood by many of us. So, okay, so why do we need economics? So the real point is what we call scarcity of resources. So scarcity of resources for economists is usually a point which you can find in the preface or introduction section of any textbook about economics. Unfortunately, this does not hold true for engineering textbooks. So the theme of scarcity of resources is usually referred to as the axiom of resource scarcity. Now, remember, an axiom is a premise so evident that it has to be accepted without any controversy. So what does the axiom of resource scarcity tells us? It actually says that the required resources are always scarce in relation to human needs and in principle satisfiable wants. So it doesn't mean that all raw resources are scarce. So for example, if you want to drink a glass of seawater, that's a resource which is abundant and not scarce. But what's usually scarce is the resources you need to build either products which people want, or even the most basic resources like water, clean air, etc., which more and more become scarce due to environment pollution and so on. Now, another thing which is important, that the scarcity of resources, this axiom is the founding axiom of economics. So no resource scarcity, then there is no need for economics. Concise definition of economics is then the study of how human society uses its scarce resources. And it immediately follows that economics is actually a science of choices. Now, many people, including me, believe that economics is actually a vital skill for the 21st century. One needs to learn. And as I pointed out earlier, after all, economic rule over the life of men, not only in the production process, but in daily life. Okay, so this is actually the counter concept of resource scarcity. This is a famous picture of Peter Bruegel, the elders from the 16th century. It's a famous or the mythical land of Pugain, where everything is there in abundance. So you may notice on the upper right corner roasted pork running around with a knife in its back to make it easier to carve some meat out of it. So in such a scenario you wouldn't need any economics. So back to our question, why as engineers we should care about economics. Now the primary answer to deal with resource scarcity is technology or technical change, how economists call it. So technology allows us, number one, to use resources more efficiently. That thus means if I have a resource to produce a certain good, then technology, next generation technology may allow me to use the same product or good with less resources. More importantly even is the fact that technology allows for resource substitution. You will see later on that this is becoming very important going forward. Now, many people have the optimistic view that technology can actually solve all problems, whatever problems and challenges mankind faces. Now, how does it relate to engineering? Engineering is really about creating technologies, and it's therefore a science which, or probably the only science and discipline which is able to mitigate resource scarcity. So from that it follows that without economics, engineering is not complete. Ultimately, one could think of the engineering objective or long-term vision to really overcome resource scarcity, at least theoretically. Okay, so I'm not sure what you...
Resources are scarce, yeah?
Okay, so I'm not sure what you did on 31st October 2011, but that date was quite important because the United Nations Population Fund reported that the whole human population on the planet reached the 7 billion mark. Now, let's look on the growth of human population over time. And again, let's look on it with our theme of resource scarcity. So what you can see is basically that in the last 200 years, there was a tremendous increase in population. So in 1804, We reached the 1 billion 1960, we reached 3 billion 1989, only 29 years later, we reached 5 billion in 2011. As I said, we get to the 7 billion mark. So that's quite a dramatic increase. The other thing to note is that since 1950, we have really consumed more resources than for all the time before, which is quite a strong signal that we need to address somehow these problems. Well, some people hope that there will be something like a post-scarcity society, but what this requires is that the population growth has to be actually limited, because if the growth continues like I had shown it in this graph, then in like the next 2,000 years, the whole population would equal the mass of this planet. And in another 6,000 years, which is a very short time frame, the whole population mass would equal the mass of the whole universe. So certainly this strong increase in population is not attainable. So the first thing to actually mitigate resource scarcity is knowledge. So knowledge is, brings us then to the knowledge-based economy. And it's really a breakthrough in mitigating resource scarcity, and therefore people or countries all over the world base more and more their economies on knowledge. So the key thing about knowledge is that it has some radically different properties compared to other resources. So number one is, if you use knowledge, you don't consume it. If you consume things, then they are gone. Like you eat an apple, then the apple is gone. You use knowledge, it's still there. It's the first property. The second radical different property is that the transfer of knowledge, if I transfer knowledge, then I still keep the same knowledge. So if I talk to you about the things which are of interest for me here, then I still have the knowledge, even though you may acquire some part of it. So this trend actually led, so in 1950 there was like 50% of the whole population in Western countries were industrial workers, people actually who make things. And in 2000, this number of people, only 50 years later, reduced to 20%, and most of the rest of the people were working in knowledge-like jobs. The third thing which is important about knowledge is that it allows you, from production point of view, to build and establish production processes virtually, meaning in the computer, before you do any step to materialize those systems. So today, if you build a skyscraper, it's done on the computer. If you build a car, it's done on the computer, etc. Which, of course, saves a lot of resources. So now let's look on this triple helix thing. It was first introduced by Escovitz and Leidesdorf somewhere 1995. The key point there is that knowledge itself doesn't really lead to a knowledge-based economy. What it requires is a close interaction between industry, government, and academia. And so only if these three dimensions work very closely together, then knowledge economy will rise. It actually arises through the interactions of those different players. Now on the lower right corner you see the UI of a program. Actually, Escovitz and Leidesdorf
not just use this as a qualitative model, but they also provided some entropy-based program which allows you, if you enter different parameters, to see how fast the economy is evolving. The way we're going to use it here is more in a qualitative model. So to dig a little bit more into the background of this, let's first have a look on transformational processes or thinking processes for this sake. So there are basically two approaches. There's a cyclical way of transformational processes and there's a linear way. In the cyclic way, you actually try to maintain a certain status and you reach the different states of your process in a continuous way again and again. In a linear or transformational process, you go from A to B and that's it. Now it turns out that neither of these ways of thinking or transformational processes occurs in reality on its own. What you always have is like a spiral or a helix model where both of these dimensions reside in a helix. And then of course the next step is if you not only have one area of concern but you have two or three, then you reside in a model which looks like this. The important thing in this model again is these black lines you see between the helices, which indicate that there is a strong communication or exchange of information between these different players. So this model you can apply on, first of all you can extend it to even more helices, and as I pointed out earlier, there's even a quantitative model behind it developed by Etzkowitz. And you can apply this model to any situation where you have nonlinear dynamics between multiple players. Okay. So now let's move to information and communication technology. Now, ICT, from my perspective, is the ultimate knowledge assimilation and dissemination engine. Obviously, it's a principle enabling technology for the knowledge-based economy, and going forward, everybody believes that it will become a basic utility of the KBE. Now, what does a basic utility is? It's like water is a basic utility you need in daily life, electricity is a basic utility, and so may ICT become basic utility. So to illustrate this a bit, if your hands starting shaking, if you lost your smartphone or have no access to it, certainly it's a basic utility for you. So the key thing about ICT is that it actually liberates the constraints of space. So before, in the 19th, 20th century, of course knowledge was kept in books, etc. So it became independent of time and independent of the era of this knowledge. The key breakthrough with information technology is the fact that it liberates space. So for example, if Peter the Great would look for how to build ships, he doesn't need to go to the Netherlands anymore, but he can just Google how those ships look like and how they have to be built. The third thing which I already mentioned in the context of knowledge is that ICT allows for virtual design and production processes. Meaning before we do anything material, we can simulate, analyze, optimize those things in the computer. So what are the top trends for ICT? I'm not going to go into detail here, but what you see listed is what Gartner, one of the leading consulting companies for ICT, listed for the top ICT trends in 2013. For example, Gary talked yesterday about IT for universities. So if you look on hybrid IT and cloud computing, then this indicates that there is a change in the role of the IT departments, which demands actually a bigger role in coordinating IT-related activities. Now, we also learned about actionable analytics and strategic big data in the context of what the National Security Agency, the NSA, and the US is doing and making all of us transparent. Okay, so these things are certainly important trends, but I was thinking about what are a little bit more long-term and more fundamental ICT challenges. And obviously, the industry has to come up with new slogans, new labels to indicate some kind of a progress. But I think what's more interesting is what are the underlying challenges, and I structured them according to the conference scheme in educational, research and industrial challenges. So that's my personal view, but at least I wanted to present this here. So the first one is actually on an educational dimension. I think the most important point is that, that we start to teach people not only in computer science but across all different disciplines, even our kids, on computational thinking, and I will explain this a little bit more in a minute. So the second dimension is research. And for research, I think the biggest challenge in ICT terms is complexity engineering. And then last but not least, the number one industrial challenge is ubiquitous computing. Now, all of these things are not new. So, for example, ubiquitous computing is around like the theme like 1990 and was brought up by Mark Weiser from the Xerox Labs, but we are still light years away from having this in reality as it was envisioned. So computational thinking. Computational thinking is about two A's. It's basically about abstraction and automation. So on the abstraction level, computational thinking is a term which indicates that in the way of thinking computational, you operate at different level on abstraction simultaneously or concurrently. Second point is that you are explicit about the relationships between those levels of abstraction. Now, then on the automating side, it's about mechanizing those abstractions, meaning making them accessible or executable for some kind of underlying meshing. It's not necessarily computer. It could be also a human who is the computing engine. The important thing is, however, that approaching things this way, you are much more in a position of utilizing knowledge from computer science to address or solve problems you have. And with the next theme of complexity engineering, you will probably recognize this. This is a very fundamental ability or knowledge you have to have. Now, last comment on this, the theme is, if you want to inform yourself a little bit more, the theme was brought up by Professor Janet Wing from the Carnegie Mellon University in something like 2006. And her belief is that computational thinking will be, by mid of this century, one of the most important skills people have to have, like arithmetics, like writing or reading. So, the next thing is complexity engineering in terms of research. So, actually, as engineers or even computer scientists, we are trained to think in terms of reducible systems, meaning systems which consist out of components and interactions between components which are well understood. So, meaning components can be characterized in their behavior completely, as can be the relationships. In complexity engineering, you have a situation where this doesn't hold true anymore. So you have like environmental changes, you have changes of the composition of the system, you have changes in the user requirements which make it very hard to actually characterize such a system as a reducible system. So to illustrate this a little bit more, if you have a system and that system has, let's say, n system states, then in classical engineering you can control every one of these n states. Complexity engineering, that doesn't hold true anymore. You may be only able to control a subset of those states. One of the direct consequences of this is that you need to introduce statistics as a main design tool for such systems. So, with respect to ICT, there is a European Union program, it's called Future ICT, that involves actually thousands of scientists who work together to create something which is called global system science. And the background is to understand better how our society is actually, or information society is actually evolving and going to develop forward. The Anthropocene, that's a theme which is like we are living in the age of Anthropocene, meaning an age where globalization and all these things play an important role. So then, let me give you one more example why this complexity engineering is so important. And it has to be noted that it's at a very early state. So there's a lot of research work to be done. So what you see here is a risk interconnection map, which tries to indicate the different relationships between different possible events in the system. And actually what you can see is that there is a very high interconnection between these different players. Now, more importantly, and that makes it a real risk thing, is there are interconnections between those different players which you don't know about. So those interconnections may result then in some kind of a system failure. So if you think about the last financial meltdown, then this is exactly the result of those risks. Okay, last thing is ubiquitous computing. Now, Mark Weiser defines this as ubiquitous computing as a method of enhancing computer use by making many computers available throughout the physical environment, but making them effectively invisible to the user. And this is exactly the point, that you will be surrounded by computing devices, but you basically will no more directly interact with them. So this is truly a very, very long-term vision. Why I think it's an industrial challenge is simply because many of those requirements, even though they are research related, eventually making this reality in daily life requires the industry to make this cost-effective solutions. This is very shortly repeating the theme of the triple helix in terms of the points we just discussed. So computational thinking, complexity engineering, and ubiquitous computing are very closely related to each other, and progress is only possible if knowledge between those trends is exchanged. Now let's add bio to the equation. And the important thing about bio is that this resource is relatively easy to renewable. So think back about our entry of the discussions about resource scarcity. So we have like knowledge as a usable but not consumed resources. Now unfortunately you can't eat knowledge, so you still need another mechanism to make to cope with resource scarcity, and in this case it's basically the bio dimension, which gives rise to the hopes that we can mitigate this resource scarcity even more. So the long-term vision there is something which is called bioeconomy, or more precisely as the OECD and the European Union define it, a knowledge-based bioeconomy. So the key thing here is that biological resources such as plant, animals and microorganisms are the base materials or resources for producing our goods and things we need for daily life. So the principal technology to make this possible is what is called biotechnology. So biotechnology is a term which is based on three Greek words, like bios, which equals life, like technos, which means tools, and logos, which is the study of. So biotechnology can be translated like the study of living tools. Fundamentally what it is the application of science and technology to living organisms, or parts of them, as a basis for the production of the goods and services we need in daily life. Now, funny enough, biotechnology is not actually a new technology. It's perhaps one of the oldest technology as we have in humanity is using. So what you see here is an Egyptian wooden model of people who making here. On the right side you see these stones. This is actually the oldest known recipe for making beers, and it's found in the context of the Sumerians. So biotechnology reaches back 5,000 years ago. Now modern biotechnology looks a little bit like this. You see the color scheme there. This is the way biotechnology is structured today. So red is for pharmacy and medicine. White is for industrial biotechnology, for example, to produce enzymes which allow the production of fuels, etc. Green biotechnology is agriculture, things like that. Blue stands for marine biotechnology, black for bioterrorism and how to deal with this, and gray stands for environment biotechnology. You already can see that there's a huge industry across these different areas at play, and already today biotechnology plays an important role. So one of the key things there is indicated by the green trash can, that many of the progress in this biotechnology areas is done by trial and error kind of research. So it's very expensive, and there is still very little engineering in these processes. So the question is then, how can we move to a future biotechnology which in essence allows us to design and engineering biotech products much more in a structured way. Okay, how does future biotechnology is going to look like? So this is a picture which indicates a vision of what can be done with future biotechnology. So you see on the top of the chart there's sunlight, there's plant biomass, there's carbon dioxide, and in the middle you see a cell which is able to take these resources and produces out of them bioenergy, pharmaceuticals, and substitutes for petrochemicals. Now, to utilize a cell for this, you need to reprogram the way it operates. And we'll talk a little bit about this later. So what you are really going to do is you have to reprogram the genetic code of those cells, and then the cell is able, hopefully, to support you in producing those goods. Now, to understand the background of this, we need to understand a little bit more the basics of life. So first off, life is very, very old. So you see 4.5 billion years ago it was formed, and only 1 billion years later already the first cells were created. Then 2.1 billion later you have multicellular organisms, and at the very end, these small 200,000 years is basically the time since we are around. Now life is very strong because 3.4 billion years ago, Earth looked like this. Very hostile environment, oxygen free, but still life formed under those conditions. If you look today on life, it's really abundant. This is what you can see in a drop of seawater, known as plankton. And as you can see, there is all kinds of forms of life. In an IT sense, you could say these are all applications of life. So this one actually is a slide which indicates the complexity of life. So I didn't go in all details, but you see the spatial dimensions on the top and the temporal dimensions on the bottom. So life-relevant processes go from femtoseconds to billion of years. Spatial dimensions of relevance go from angstroms to 10 meters. The area of 10 meters, and if you take ecosystems, then it's even bigger. So you have huge orders of magnitudes between the processes you have to look on if you want to understand life. if you want to play around with this, there is Harvard provides actually a site which is called BioNumber, so you can just put in something like what is the length of an hydrogen bond, and it's going to come back and tell you it's 2.5 angstrom. Okay. Now let's look on the ICT dimension of life. So you may remember your education in school. So basically life is a foundation or a function of these four bases: thymine, cytosine, guanine and adenine. It's actually a digital alphabet, and maybe biology is the only science which is based on a digital alphabet. Now, if you look on these bases, then you can see each has a different shape, and actually we look on them in two ways. One is from the top, and then one from the side, and on the side you can see that these molecules are very, very flat. Now, then, the code of life is storage in the DNA, which is actually a string consisting out of these different bases. So, unfortunately, things are not that easy. You may remember again your school time. So basically, the DNA is a double helix, which is a quite complex three-dimensional molecule, but anyway, it's a very core. It's based on these four letters. This is a picture which was published recently. It shows you a transmission electron microscope image of a DNA. So if we now look on the DNA, we have sequences of these four letters, but it doesn't tell us really anything. It's like you have a sequence of zeros and ones. So unless you are able to decode these letters, it's not really a lot of information you have. So if you look on the other spectrum, then you have something which is called proteins. Proteins are basically the workhorses of life. We consist to a large extent of proteins, and the key thing is proteins are sequences or chains of what is called amino acids. And these amino acids form a second alphabet. Here you can see there's like 20 amino acids, and each of those amino acids is assigned a letter. So again, you have a digital alphabet. Then there is an intermediate step which forms the third alphabet, which is called RNA. So RNA actually comes into the play if you read the information in the DNA, then you read certain sequences, and these sequences are stored in the RNA, and the RNA is then transported to something which is called ribosomes, which then create the proteins. So here you have the whole program, which is called Central Dogma of Molecular Biology. You have the DNA, the DNA is translated in RNA, so then in the RNA, three letters always translate into one amino acid, and that gives you the programming. So the whole thing looks really like a program. Now, the perhaps smallest or level of abstraction which is autonomous in terms of living is cells, and these are singular cells, bacteria. The one shown here is Escherichia coli, which is the human gut bacteria. And as you can see, on the right side, there is the DNA stored in the nucleate DNA, and there's also certain parts stored in the plasmid DNA. Then you have these red points, which are ribosomes, which are basically responsible for the translation process to proteins. Now, cells are heavily integrated networks. And this picture, what it shows is cells can take on external signals. Then there is something like in blue, which is called a single transduction network. In this network, the information gets interpreted and certain proteins are created, which then interact with what's called gene regulatory network. And here's green boxes. And these green boxes produce then enzymes or certain molecules which enable the metabolic process, which is responsible for creating growth and energy and life sustaining chemicals. Now, what a key important property of life is that it is able to self-replicate, and actually in dramatic dimensions. So if you take one of these E. coli bacteria, then it doubles every 20 minutes. Now, after 10 hours, you're already going to have 1 billion of those bacteria. And if there is good conditions for them, they're going to double further. So after 36 hours, you have a 31 centimeter layer across the whole world of E. coli, and after 38 hours, this layer would decrease to 2.5 meters. So this is a graph that shows, well, animation that shows how fast the population of those bacteria is growing. Now, to summarize, whatever an intermediate summarization. So, first statement is biology is an information science, and bring it very closely to ICT. The second result is, in principle, bacteria are application-specific processors. So they take input, they generate output. So it's like any processor you are aware of. However, there's a very important additional dimension is bacteria are self-replicating micro-machines. So what they basically can do, they can take molecules and can build themselves up from these molecules. That's, by the way, something which is people in nanotechnology are looking for, to build these nanofactories which can take up molecules from the air and create any device you want. Okay, now let's move to synthetic biology. So synthetic biology is defined as the design and construction of new biological parts, devices and systems on one hand, or the redesign and construction of new biological systems for useful purposes. And the key thing is that this is be done in a forward engineering way. So here's an example to explain the analogy between electronic design and synthetic biology. So you start off on the electronic design. You have a physical layer consisting out of transistors and capacitors on the one. You go to gates, then you go to modules, computers and networks. You have a similar hierarchy in biology. You have proteins and genes. You have then biochemical reactions, and the next level are pathways which behave like models. Then you go to cells and finally to tissues, cultures, and eventually you would end up with organisms. So what I already mentioned earlier, based on the ability to program DNA, you will find certain circuits in life, or you can even build one. This one is an example for a delay circuit. It's actually a sequential oppression cascade. So you have three nucleus. In this kind of sense, it's enzymes. So what happens is these T-shaped symbols actually mean that the occurrence of X suppresses the enzyme Y, and then the occurrence of Y suppresses the enzyme Z. So it takes always some time for one of these enzymes to increase or decrease. And basically this way you can design a delay device. This is a little bit more complex. Again, we have three biological entities, enzymes or proteins, X, Y, Z, and in this case you build an AND-gate filter. So what you can see is there's only a small spike in terms of time of the enzyme X, then this spike gets filtered out. Only if there is a certain width of the signal, then the circuit function should function as it is. This is just another example. If you look on the right side, there is a biosensor. What this biosensor actually does is, if salicide, that's a certain eyesight, and area beneath, which is a sugar available, then these circuit acts as an AND gate and creates some output. In this case, it's a green fluorescence protein which is created. And you can imagine that if you are able to create more complex circuits, that you can certainly build something like embedded processors which are able to operate or fulfill even more complex functions. So one very important thing for synthetic biology to become real is the ability to read DNA and to write DNA. On the left side you see the ability to read DNA. So over the years it started by hand, and then there were these big machines. Now today you see this minion device, which is like a USB stick, which you can buy for roughly $1,000, and this device allows you to read DNA. So it's a dramatic technological progress. On the right side, things are, this is the area of synthesizing DNA. So if you want to build your own DNA, then you need the ability to create this DNA. And again, you can see that the cost, that's a yellow graph actually, that the cost of creating DNA went down. In fact, today there are companies you can then just send a string of ACTGs, your own DNA, whatever it is, and they're going to create it and send it you back by mail. So, and that's in an affordable way. So these are the visions of biotechnology, synthetic biology. Some of them are fiction, some of them are already reality. So, for example, in the lower left corner, I don't know who of you knows these science fiction series Farscape, but the funny thing there is the spaceship is actually a biological system, so it behaves like a biological system. On the top you can see a synthetic archon, so the idea is here, if you can program cells in a way that you can build even houses based on the genetic code we build. And then there are the other examples. I'm not going to go in detail, but there are some real examples, things which are already function today. And so for example, the MIT was able to create a synthetic analog computer. Analog computers were basically the computers in place and used before digital computers. Now these days they were able to create such a computer in a bacterial cell, and then there is these you can see this glowing plant project. So this is a group of people who decided to use the firefly gene, which is responsible for the light of the firefly, takes this gene and build it into plants, and then having lightning trees or roses or whatsoever. Now how real this is, I don't know, but they managed to raise like close to $500,000 in crowdfunding raise. So crowdfunding is like you go with your project, you explain your project, and then people can decide whether they put $10 in, 20 or whatever. Now in this case they made quite a lot of money. So it still remains to be shown that you can have a glowing rose. But you can see there's a lot of movement in this area. Now, given this, we should now walk off, go into our garage, graft some DNA, and build some biological systems. Fortunately or unfortunately, this is still much more fiction than reality. The simple reason is that biological systems are extremely complex, and I'm going to show in the next few slides. Then I finish just to give you a feel how complex things are. This, for example, shows two DNA strands, and as I pointed out earlier, DNA can self-replicating. So left you have a cartoon, on the right you have a three-dimensional model, which is actually only the structure of those molecules involved for the self-replication. This is how it looks again if DNA or if RNA is produced from DNA. And the ribbon models you see there doesn't really show each atom of the molecule, it just shows the backbone, and already this is a highly complex structure. This one shows if you have the RNA that I mentioned earlier, there are these ribosomes, and these ribosomes read the RNA and then create proteins. Now these things on the cartoon you see down is there are all these chemical elements which transport amino acids to the ribosome, and then you can see that there is step by step a protein created. Now on the upper right you get an impression how complex these molecules executing this process are. This is an example for a molecule, it's myoglobin. On the left upper side you see John Kendrew building by hand a model of this molecule. And the result is then seen in the middle, and right there's a computer thing. So proteins, very fastly, are highly complex systems. So they are based, as we learned, on an alphabet of 20 amino acids. But if you think about, if you have a chain length of 2 amino acids only, then you already have 400 possible arrangements. If you take 10, you end up at something like 10 trillion possibilities of possible proteins. If we take the length of 100, which is the average size of proteins anyway, in nature, then you're going to have 1.3 multiplied by 10 to the power of 130 possible protein structures. Now note that the total number of protons in the universe is only 10 or 80, so that's unbelievable combinatorial complexity which is possible with proteins, and the known number of proteins is extremely small compared to the possible numbers. This is how it looks like if you had dinner or lunch. So that actually shows the metabolic processes which are happening in your body to process the food you have eaten, etc. So it's called metabolism. And this is a slide which shows that actually we don't really deal with separate entities, but we have kind of a molecular soup we are operating in if we want to build synthetic devices. So the whole point is synthetic biology is extremely important, but it's only the next thing after the next. There's so much complexity still to be dealt with that it is still going to take quite some time. Now to conclude the presentation, just another helix. In this case, what we learned so far is that the knowledge-based bioeconomy is our only hope to mitigate the scarcity of resources. Then we learned that biotechnology is the key principle enabling technology, but without synthetic biology, this is not going to succeed. And obviously, all of these processes need a lot of ICT support, but more interestingly, you also may got an impression that synthetic biology may become the next ICT if we can use these processing capabilities of cells and DNA and etc. more knowledgeably. Okay. Any questions? If you want to have this presentation or you have any questions, just drop me an email and I'm more than happy to send you a version.
Okay, thank you very much indeed. Very nice, interesting, enlightening talk. We still have time for a couple of questions, please. Any questions? Please, Frederick?
How much of that is hype and how much of that is reality? Because we have had a lot of things about quantum computers, about light routers that would... so quantum computers, you encode binary digit into using quantum theory. The other one, you can encode it using lights. Here you encode information using cells. So how much of this is reality and how much of this is just hype?
Okay, so that's obviously relative to time. Most of the things I showed on these possible application sites are hype. However, that hype may very well turn into reality over the next 50 years or so. Certain elements like personalized medicine or the creation of biofuels based on reprogrammed organisms are reality. There's another very famous example around in medicine which is called artemisinin. So the Bill and Melinda Gates Foundation actually supported the program to create, utilizing synthetic biology procedures and medicine for malaria. The point with malaria is they're suffering like 200 million people every year. And the only known medicine to deal with this is artemisinin, and this is one which comes from certain plants. So what you have is always a problem of enough medicine because it just gets too expensive. So there was a company supported by this foundation, Gates Foundation, to create a synthetic artemisinin medicine, and actually they succeeded. And that's basically a huge impact for these 200 million people to have this medicine more easily available. Now, having a starship as a biological system is certainly still fiction. Huh? Fuels are definitely... So the challenge with fuels right now is to make it cost effective. Still, unfortunately, costs more to create synthetic fuels than to utilize dead carbon like oil. But I think it's a question of time. Now, in the US, which is, I don't know, but the US really spends huge amounts of money in research around synthetic biology. For example, to make these fuels commercially, or give commercial support to the companies who create these synthetic biology fuels, the army is required to buy a certain amount of those fuels from these companies. So I would say lots of hype, but there is a solid layer. Last comment on this, and that's what I was trying to show in these other slides, the complexities are still huge, and the degree of ignorance in this area is still extremely high. That's why I said it's the next thing after the next. But it's a necessary thing which has to happen.
Okay. Last question, please. Yes, please.
Tom, please, do you cooperate with any medical laboratories in the field of gene engineering? And then you know something about some laboratories which work in the field of this sphere and which can help to influence the wrong gene in some genetic illnesses, especially?
Did you I will repeat the question. Did you cooperate with any genetics laboratories?
Yes.
Do you know some of them who are able to identify and to mitigate a bad gene in the sequence?
Okay. So do we work with, I would say, synthetic biology labs which are able to change genes, etc.? Yes. On research, we have a research collaboration, for example, with the Ludwig Maximilian University in Munich. Practically people are able today to replace genes, and you may have heard about the gene therapy efforts. The results are still, I would say, not satisfiable because it's still not understood. So the thing with genes is not so easy. It's not just you have one seed gene and then you have a certain behavior. In reality, in many cases, you have multiple genes somehow interact and create this behavior. That's the most famous example of the gene thing is perhaps insulin. So, insulin is exactly produced based on one gene. So in this case, you're going to be quite successful for medical purposes. But in many other cases, it's still at its infancy.
Okay, and the very last question, please.
Could I come to Mike, please?
Yeah.
My question to you is, well, when I listen to you, there are three different aspects that you started talking about. One of them is the economics. So let us put economics in one box. Okay. And then you talk about the triple helix, where you have industry, government, and academia. So let's put that in one box. So you have two boxes. Economics in one box, the triple helix. When you talk about the ICT, you talked about three components: computational engineering, then ubiquitous computing, and then you talked about complexity engineering, right? There are three things. So this is in another box. I just want to know what is the interaction among the things in each box and how these boxes should interact and what is the goal of interaction, what is it, or what is the complexity of the overall interaction and what is the outcome of the whole thing, which I'm not able to understand. I would appreciate if you could explain that. Thank you.
Yeah, and I would really appreciate a short answer because we're behind our schedule. Thanks.
So the short answer is economics drives everything. So whatever happens in these other distances or in these other occasions is based on economics. Now, the 3 points I brought up, computational thinking, etc., are key points for ICT, but even more key points for biology. So the idea here is that ICT really is important for driving these things so that they can be used in a biological context. The triple helix is just a model. So if you have you can apply it to any situation where you have different areas which have to interact to create a certain outcome.
Okay, thanks again. And unfortunately, due to the growing and lasting interest to this very good talk, we are behind the schedule and will miss the coffee break. And this is why I hand over to my colleague Grigor Zoltkevich for the next section immediately. Oh, it's up to you. You may announce a 5-minute break. To let Frederick prepare himself. And let
Good morning. Today we have a tutorial Associate Professor of University of Nice, Safia Antipolis. Today's tutorial devoted to human profile for Martin. Please, thank you.
Thank you, Gregory. So I'm going to talk about this profile that we call it MALTE. MALTE is about real-time embedded systems. So I don't know how much of you knows about real-time embedded systems. I was not sure, so I will try to focus on simple things and not to spend much time on technical aspects. So there is a website here, omgmalte.org, where you have all the information about the profile. There is also a tutorial on this website, an official tutorial made by people at OMG. And the official tutorial about MALTE lasts 2 days. So I don't think we have 2 days now, so I had to skip a lot and really to focus on one part of it, well, one small part of it, which is the time model of MALTE. And since I'm a scholar and I'm not trying to sell you anything from OMG, I will focus on the part that are more interesting to me and that are related to research activity. So, but if you want to know more about MALTE, feel free to go there. You can download the tutorial and you will have all the information you need about this profile. So this is the agenda for my talk. I will give you a very, very brief overview of Marte, what are the big pieces and where you can find the information. Because Marte is a profile, I know most of you know about UML. I'm not sure how much you know about profiling mechanisms, so we wanted also to introduce this mechanism that was designed to extend UML specification. So I will talk about Marte, about how we can extend UML through profile, and then I go on the main part, which is the time model and something aside that is that we call the constraint specification language. And if I have time, then I go to application of that. So the first thing is, Marte is about modeling and analysis of real-time embedded systems. So modeling is something that is very active in research now around model-driven engineering. I will come back to that in a moment. Analysis, when we talk about analysis, that means we need formal models to do the analysis. And when I talk about analysis in the context of Marte, I specifically mean two kinds of analysis. First one is schedulability analysis. Schedulability analysis is you have an application, a software application, and you want to know if this application will be schedulable on a given computer, on a given processor. The second kind of analysis we do is performance analysis. Performance analysis, some people call it simulation. You have also estimation of bandwidth and the actual performance of the software to run on a particular platform. Because I talk about real-time in this context means that the time is as important as the function itself. So in the past, a lot of people, I mean, famous people, used to think that the function was the main thing in designing a computer system. In real-time system, function is not all. In your car, for instance, you have a braking system, and if you brake, but you don't brake fast enough, then you don't care that you've broken because you're right into the wall, and then it's no good for you. So in real-time system, the main thing is that the time is as important as a function, and even more sometimes. You prefer to have things on time, doing almost what you want, rather than doing exactly what you want, but doing that late. The last part is embedded systems. Some embedded systems have nothing to do with real time. What I mean by embedded systems is systems where the execution platform matters. So you're not just computer scientists that do programming, you also need to know about which processor, which platform will execute your system. And so in Marte we have parts about analysis, we have parts about real time, and we have parts about the platforms, the resources on which the computer system will run. So I said the first part is about model, and here I mean essentially engineering models. What we try to do is to mix them with formal models, but I'll not speak a lot about that. So engineering models is what you intend with by engineering models is something that is abstract. A lot of people try to do models that replace the program, but if you replace the program, it's no use. So you need to be abstract, focus on one specific element. It needs to be understandable, and usually that means graphical. In presentation, if you have graphic information, you are usually able to catch the information much quicker than when you have to read a long program for that. Then it has to be accurate. Accurate means that you can predict something, you can do something with the model, which goes also to the predictive part, where you can do analysis and get answers without having to use the actual system. And the last property is it has to be inexpensive. Inexpensive means that if you spend as much money to build your model, then as much money to build the model as you would do to build the actual system, then it's no use, and rather build the system itself. So it has to be inexpensive. Now, engineering model, I spoke about model-driven engineering, and I suspect most of you know about software engineering. So the question is, what is the relationship between model-driven engineering and software engineering? So I don't know if you're familiar with model-driven engineering. It's really a very active research things, and the idea here is that model-driven engineering is for software engineering. Is an engineering discipline that tries to find solutions for software engineers, not for the users. When you are software engineer, you try to build systems for the end user. When you are a model-driven engineer, you try to build systems for the software engineer so that they will be able to build computer system faster, software system faster. And what this is about building models, so like smart models, from which you can generate code, generate parsers, generate compilers, generate editor. I mean, generate by pressing a button. I don't mean spending 1 week to build a parser, while this has been done by engineers over the last 30 years. Now we have technologies to produce the compilers very, very, very quickly and not spend a week to do that. So that was generic about model-driven engineering and about Marte. In the domain, there have been other standards, other profile. So since you're not probably all familiar with the system, I would skip that part. But you have to know that there are other specifications, and Marte has some relation with that. These were the guys that designed the Marte profile. So they were a whole bunch of academics, but there was also a whole bunch of tool vendors and of industrial guys. At the beginning, there was only mainly French people, and at the end, we ended up with quite a lot of representation. And now, when you buy a UML tool, that's why you need tool vendors. When you buy a UML tool, any major tool has implemented Marte in the tool. So if you have a tool that you use to do UML model, if you don't do it with tools, you do it on paper, then I'm not sure you're doing UML models. So if you actually use a tool, then you should check somewhere you should have Marte implemented in the tool. So everything I will say, you can right away try to use it in your tool. This is about history of Marte. So a profile at OMG. OMG is Object Management Group, is the consortium that specify systems around UML, around Corba. And when you started to do a profile with them, it takes a long time. So now we are in 2013, but all these things started in 2005, and even earlier than that. And we only reached the first release of Marte in 2009, that means 5 years later. And now we are speaking about Marte V2, so I hope what I'm saying now about Marte V1 will still be valuable for in the next year. So as I promised, I will start by explaining what the profile is. How many of you have already used the profile? I mean, I suspect most of you have used UML somehow, but how many have used the profile? Yeah, so no end at all. So I take just 2 or 3 slides to say what that is and what are stereotypes, otherwise everything I say after that is just useless. So let's take an example. This one is a very simple example. This is a state machine, a UML state machine, and this state machine is just a blinker, something that puts the light on and off every 10 something. And 10 something is really the point. This is standard UML model. everybody thinks that, assume that this is after 10 seconds, because if you speak of a blinker that blinks every 10 hours, then I'm not sure you have any use of it. So everybody assumes that 10 is about 10 seconds, because everybody wants to have a physical relation of time. And this is precisely what we were fighting against, and I will come back later. In our mind, time is not only physical, but you need to be precise on what kind of time you use. And even if you use a UML model like that, you need to say what 10 is about. You need to say whether it's seconds, hours, or something else. And I'll show example where it can be something else later. But now let's assume that it is physical time. I want to be specific about what this 10 things is. So what UML proposes is, if you know the vocabulary of UML, then you will be able to catch the right vocabulary, the right words, and modify the meaning of these words. So first thing, you have to know that this is a UML state machine, it's a behavior. Then you have to know that you have a transition, and on transition you have triggers. So basically what you have to do is you have to look at the meta model of UML, and you will find this keyword somewhere where you have a transition here, transition being that row, and a transition as a trigger. It can have many triggers actually. A trigger is related to an event, and events, you can have many kinds of events, but in that case you have this keyword here after. That means you have been using a time event, an event where you have a time specification. And time specification is given here as a value specification. So you need first, if you want to do a profile or use a profile, you need first to know the vocabulary. And this is the vocabulary. You have diagrams that explain what the vocabulary is. Now once you have that, you can decide to create an extension of this vocabulary, to create new keywords that are specific to a given domain. So if the domain here is to speak about physical time, I can add here, for instance, I can add something I call stereotype, and this stereotype extends the notion of trigger by adding an attribute, which is a particular unit. So this is not the way we did it in Martin, because we did something much more complex than that. But this is a kind of simple idea of what you could do. So you must notice that this row is different from this one. This is not specialization. This is specialization. This one is extension. Special row that is used to say that you want to extend to add new keywords to your language. Okay, once you've done that, then you can apply the stereotype on the model. So you have your state machine, and on this trigger here, you apply your stereotype with the same name as the one of the stereotype, and then you can add a unit. And so you can say this is not second, as I suggested before, but this is 10 milliseconds. And you can apply it again, and then apply it again, then you say that this one is every 10 minutes, for instance. And now you know somehow what you're talking about. You know precisely what this 10 means. Okay, so you understood that the stereotype is that, a new keyword. A profile is just a set of stereotypes that will define new keyword that will restrict the one you are allowed to use for the sake of modeling a particular domain. Martin is a profile like that, a set of stereotypes. And if you have your UML tool, you will find all the stereotypes I speak about in your tool. That allows you to take a normal UML model and put just the right vocabulary inside. So this is how Martin is done. Martin is 600 pages long, so I don't have time to go through all of them. What we did is we did it in 3 parts. A part that is called foundations, and in foundations we have 5 main chapters. Then we have 1 part for the design and 1 part for the analysis. So I put in red the two main chapters that we were in charge of. So we were in charge at the idea of doing the time model, the time chapter, and the allocation chapter. That's why I'm going to speak more about the time chapter than about anything else. But before going to the time chapter, I just want you to have a rough idea of what is in the other chapters. So I talk a bit about NFP, non-functional properties, in real-time system, embedded system, non-functional properties are critical. I also speak a bit about hardware resources, and I also speak mostly about analysis, very, very briefly. So non-functional properties, it's everything that is not functional. So usually people think of time, but there are many, many examples of non-functional properties. And when you design a system, the function is not all. What you learn at school is you have to know how to do the function right. But when you go to the industry, then they say function is one part, maybe 10% of the effort, and everything else is the most difficult part. When you want to build a phone, for instance, you're not happy to pay your phone 600 euros, but if people didn't take care of non-functional properties, you would pay 6,000 euros. And so really, really non-functional properties are important. So example of non-functional property is the cost. When you want to build a system, a phone, you have to take into account the cost of the system. Another very important non-functional property is power consumption. And we had talk from someone from microelectronic industry. I mean, power is really, really a key things in microelectronics, because when you have your phone, you want to be able to use it and not have to plug it in the electrical plug every 10 minutes. I mean, if you think about your phone, the most annoying thing is in the middle of the day, no battery dead, you cannot use it anymore. So the way they drive the design is by assuming that you at least want your phone to work during your whole day, and they have classical usage of phones, like I do 2 hours of Facebook, I do some kind of LinkedIn, I do some web, I do some phone, I do something like that. And then at the end of the day, I still want to have some battery if I have an emergency and I have to call someone to get me around. So the way they do that is really that. And to do that, you need to have this property inside. If you have something like 10, it's supposed to represent power, but you don't know what unit it is, it's no use to you. So the non-functional part of Marty has done something like that. You cannot read most of it, but you can try to imagine what it is. It's what people call dimension analysis. The engineers, the system engineers, they like to do dimension analysis, which is to be sure that when they write formulas, they are consistent. So when you write a formula where you have time, you have another formula where you have length, you have another formula where you have power, you want to be sure that when you put the things together, they are consistent, and you need the dimension and the unit to do that. So one part of Marte, the non-functional part, has defined a set of dimensions that are useful in real-time embedded systems, and you can reuse them. So what you see, you have something that is called, for instance, you have something that is called energy, unit time. You have also time, unit time. You have something that is called frequency, unit time, frequency. And obviously there is a relationship between frequency and time. Frequency is 1/time. So you have here, you have explicitly the relationship there is between frequency and time using these annotations here. So you have also the area. The area is very important, and data transfer, and so on and so on. So there is a whole library of stereotypes that gives you just the dimensions that you might need to design a system. You have also a set of types, so once you have the dimension, you'll be able to use them by typing the data. So you'll be able to type and to, for instance, say that this value, this 10, is the frequency. So it's 10 Hz, for instance, or 10 megahertz or 10 gigahertz, you have to choose your unit. And to do that, you need special time. So for each dimension and each kind of unit, you have a special type that will allow you to type the system. That's all I say about non-functional property. This is really, really, really important in embedded system. You need to know what are the dimensions and what is the type of the values. The other thing is, I hope you can see, I'm not sure you can, but I help you to understand what is inside. The other thing important are the resources. When you want to do with performance analysis, you need to know how many resources you have, how many processors you have. So now, it used to be easy. Everybody would have one processor, but now in all systems, you have many. Even in your phone, I mean, if you have one of the latest smartphones, you have processors that are 10 times faster or more powerful than the one we had on our desk not so long ago. And even in a mobile phone, you have multi-core processors. So you need to have a precise description of the resources of your application. If you design software for a phone, it's not the same as if you design a software for a parallel center that have a lot of resources. So you have a whole chapter that is called generic resource modeling, and that just describes the resources that are available, how many processors, what kind of memory you have, what kind of bandwidth you have, and so on and so on. So this is just a small example of that, where you have two computing resources, and you have a bus, CAN buses, and you identify what are the different things, and you identify the devices and the bus and the memories and the size of the memories in your architecture. So this is something that we call generic resource modeling. Then you have also the description of the hardware resources. So you have a set of stereotypes that identify that you have a processor, that you have RAM or ROM or a kind of memory, that you have devices, different kinds of devices, that you have different kinds of communication units, and that you have timing resources somewhere. So I'm not going too much into detail here. That was just to give you that the two main things in my point of view for the multi except time was that you need to have dimensions, you need to have types, and you need to have a precise identification of available resources. Now I go to the time model. So time model, it's large also, it's a big chapter, but I try to focus on three main aspects of the time model. And just first to introduce, when you speak about time, you usually think physical time. And so we took this painting from Salvador Dali to illustrate why we didn't want to only think about physical time. So these things represent clocks. In the head of Salvador Dali, this painting was just to recall people about relativity between time and space. And in modern systems, we really have this kind of effects where if you have distributed systems over the planet, I mean, in between, you have a network between France and or Europe, Ukraine, Asia, United States, you cannot expect all the systems to work at the same time. So you have some lag, some shift in the way you measure time, and you cannot rely on the time measure itself. So you really have some strange effect, and you have time that stretch a lot, that slow down sometimes, that go faster some of the time. And to show this stretch effect, we thought that these clocks were really representing that thing. So the stretch effect is what we call logical time. So every time I say the word time in the future, it's about logical time. And I show how this is related to physical time, but I mainly speak about logical time. Then I've added a word before, multiform time. Multiform time is that usually engineers, they don't only use seconds or hours as a measure of time. They also use other kind of time reference. So to illustrate that, I have this simple example here. So you all have a car, you all have a slot engine in your car. So you must probably understand what I'm saying here. So some time ago we had to design a safety system for an engine, and we took the specification from Bosch. Bosch is a major manufacturer of pieces for cars, for automotives. And in the specification of the engine, of the security system of the engine, there was never a single time second as a unit. They were never ever referring to seconds in their specification. And this is very simple. There is a very simple reason for that. So the security system, I'm not entering into the details, but the thing is, you have to decide when you open the valve. This is a computer that does that in your car. The computer decides when you open the valve. You open the valve either to let air fill in or to let the gas flow out. But you have to decide very, very precisely when you do that. So you would think this is physical time, but actually it's not, because if you think in terms of physical time, it depends on the rotation speed of the engine. And you don't know what the rotation speed of the engine is. It's really, really complex equation that tells you how fast the engine rotates. So instead of saying that, you have a very good reference that is not the rotation speed, but which is the rotation angle of the crankshaft. The crankshaft is that thing that rotates here and that activates the piston. And you also have a camshaft here that turns here and that activates the valve. So this is a really precise unit to measure when you have to open the valve and when you want to send the sparkle to make things explode. So all the specification from Bosch is only based on rotation angles of the crankshaft and the camshaft. So the unit is not second, the unit is rotation degree of the camshaft. And this is what we call multiform time. Multiform time is where you have different references to speak about time. You can use seconds, of course, but you can also use rotation degree of a camshaft. Another useful unit that is often used in computers is processor cycles. If you look at benchmarks on processors, most of the time you say that these things, this application takes that many cycles. And you won't say it in terms of time, because your processor, all of your processors, they have mechanism to slow down the processor when you don't have the battery plug, or to accelerate the processor when you want to overclock your system. So if you speak in terms of time, then it really depends what configuration you have. But if you speak about in processor cycle, then it's a constant reference and you can say many things about that. So really one of the main things we try to do in Marte, and I think that's one of the most important things you have to recall if you want to recall something about Marte, is that time is not only about physical dimensions, and we've tried to make it not physical by introducing this multiform time. So the way we do it is using a notion that we call clocks. And when I say clock, this is a very, very bad word in the end, but that's the way it is now. So the clock is something to measure time, but not only physical time. So for instance, what I do here, I put a clock, this is this little sign, I put a clock here. That means I want to use that event being full rotation of the camshaft, as a measure, as a unit to measure something else. I want to use that event as a measure, as a unit to measure something else, the camshaft rotation. Okay? So this is one clock for the system. Not the physical watch, physical clock. This is one clock that we decide is good to measure anything. And we can put another one, and we can have as many as we want. We put clocks everywhere in the system where we think we have relevant events that can be used to measure time. And for instance, we have a camshaft clock and we have a crankshaft clock. And in the following, we will use these clocks to design the system. And so the central notion of the time model is this notion of clock. And as you see, you have somewhere here the chronometric clock, the physical time, but you also have logical clocks that actually are discrete and that are logical. So I think I explained a lot what they are, so I hope you understood these key points about logical clocks. So in practice, concretely, in terms of metamodel facilities, we went through the UML metamodel, 600 pages or 800 pages now, and we've seen something strange in the metamodel. We have a lot of events everywhere, and only one particular event is a time event. This one is a time event. This is call event. Call event means I call a message on an I call an operation. You cannot have any time information about when you send a message. In UML, this is impossible. You have to choose either you put time information or you call a method. But you cannot do both at the same time. And this is really typical. You have 30 kind of events and only one kind that has time information. And when he has time information, he does only that, nothing else. So one thing we did is we decided to extend this notion of events, and we created stereotype we call clock that apply on any event. And this clock will serve as a reference to express timing expression in the specification. So we use any kind of events as reference to express time constraints on the system. And to the clock, we associate a unit. So we have a special stereotype that we call unit. And unit, I don't show it the zone, but it relates to what I showed before on non-functional properties. So the same example about the engine, and then you have a UML model. This is a structure class. And then you have first camshaft, this one here. Second camshaft, this one here. You have a crankshaft. You have some relation between them. And using marks, you can decide that these elements are time reference, a time basis for anything else, and you call them clocks. One other thing you have is something we call time processing. Time processing is to put time information on behavior. Behavior being state machine, being timing diagram, being scenarios, being activities diagram, and you often want to put information on that, how much this action lasts. 10 milliseconds, 10 rotation angle or something, or whatever. So we have introduced this stereotype time processing, and I'll show just a little example here. So this is a state machine that represents the four states, the fourth state of the stroke engine cycle. Intake, you take fuel, then you compress, then there is explosion, and then you release the gas. And you have, between these phases, you have a transition that is, say, after 90. And 90 is not second, but 90 is degree, rotation degree of the camshaft. And now you know that because you have this stereotype, time processing, that show you that associate the clock to that, and every time reference now refer to this particular clock. Actually, this is a very simple example, but if you look precisely in the engine, it's not working like that. And so you can have a more precise model, UML model about what's happening in the engine. And if you look carefully, you have overlapping between the four phases. You see that you have an overlapping between the intake and the compression. So during some time, you're both taking fuel and starting to compress. And in Bosch specification, you have a precise description of how long this can be. And this can be between 40 and 60 rotation degree of the crankshaft. And then the whole cycle takes 720 degrees. That means you need the crankshaft to rotate twice to have a full cycle in your engine. So using that kind of things, you can actually model the system and see what's happening in your car. Okay, so I hope that's clear. We have the clocks that are time reference, and now we have the time processing that allows you to put clocks and use clocks to express time constraints like that. And so the third stereotype, which is important in the time model, is the one called clock constraint. And so what we have is once you've done that, what you want to do is, for instance, that the camshaft is twice slower than the crankshaft. Every time this one rotates, make one rotation, one full rotation, then the crankshaft will make two full rotations. So you want to express that kind of constraints. And so what you need is you need a specification language that you will use to put relationships between these two clocks. And what we do is we propose a language that we call CCSL, Clock Constraint Specification Language, clock being in the large sense that I talked about now. And what you do is you extract those clocks, those two clocks here, CAN2 and crank, and then you put this relationship between these two clocks. And this relationship in particular say that camshaft is what's called a crankshaft, but we have many keywords to express different kinds of constraints. So this is the main content on the time model. So the remaining part is about two things. First, I wanted to give few ideas of what kind of relationship we can build using this language called constraint specification language. And second is show some kind of direct application of these things. So I think now this is a summary of the main three stereotypes I talked about. And now my talk is about the clock constraint specification language, which is a language used in this pink box here to apply constraints on clocks. So clock constraint specification language comes from this clock notion. Some of you have seen that slide yesterday during my presentation, and I won't speak much time on it. The main thing is this logical notion of time. We didn't wake up one day saying, oh, why don't we introduce logical clocks? I mean, logical clocks have been used since the 70s. I mean, since computer science exists, logical clocks have been used a lot in distributed systems, in real-time reactive systems, and there are two main concurrent or contemporary areas where logical clocks were used. And we've just tried to reuse the best from the two worlds. So the two worlds are, on one side there is distributed systems, and there is a guy called Leslie Lamport from Microsoft Research that invented the notion of logical clock, and that was there to synchronize the different pieces of the system without having a global notion of time. And the second world is synchronous languages, reactive systems. The most famous example of synchronous languages now is SCADE, which is used in the avionics industry to design Airbus plane, and where they also use this notion of logical clocks. So, as you probably understood by now, the clocks are events. In the UML terminology, clocks are events, which are a sequence of instants. Instance being the occurrence of something, the occurrence of event. And usually these sequences are infinite. So we have two kinds of relationship, the red one that you showed before and the green one that I haven't talked about. The green one directly comes from Lamport notion and from many things in literature. Basically something that people call causality relationships between events. And so there is a lot to say about that. I don't want to say too much, but basically you have two events, A and B, and you want to say that one event is caused by the other one. A causes B, or B depends on what's happened on A. So causality is untimed, so what we did is we define a new one which is called precedes, and which has a notion of time. Not only A causes B, but also A always occurs strictly before B. Okay? And then we have synchronous operators that just say when things happen at the same time. So these are the two main relationships. So based on these relationships, we had a talk yesterday about temporal logic. So you can describe a lot of these constraints using temporal logics, but what we thought is temporal logic is too difficult for engineers, and they don't want to try to understand that. So what we thought we'll do, we take these very primitive notions, and we propose some patterns, classical patterns that are relevant in real-time systems. So based on this very simple notion, we built classical patterns of real-time scheduling. And these are the main reason why we have this primitive operator in CCSN. And I talk about the primitive operator now, but the reason they are there is because they are classical patterns used in real-time systems. So these are three clocks. This is how I will represent them in the future. So I simplify, abstract them using lines. Lines saying that there is a total order between occurrences of events in the clock. So the first occurrence of C1, the second occurrence of C1. So there is a line here that you can assimilate to the physical time. So there is a total ordering between the occurrence of events of C1. And you can have three clocks like that, where you have total ordering every time. So three independent systems. They all have their own physical time, if you would. But there is no a priori relationship between them. So they are all working independently of each other. And this is really important. Multi-clock systems have clocks that work independently of each other without any synchronization mechanism. Once we assume that, then we can use the two kinds of relations that I showed before to put constraints on them. And so these are clocks, these are the instant, and then we define these three relationships. We can say that these things is simultaneous with that happen at the same time. We have this precedence relationship that says these things always occur before that one. Maybe because this one is sending a message and this one is receiving it. So if you receive this message sent by this guy, you have to happen after. The reception happens after the sending. And you also have this relation I didn't talk about, which is a kind of synchronous relation that says they cannot happen at the same time. So this is exclusion relationship. These two things cannot happen at the same time. Either one happen before the other one, or the contrary, but they cannot happen at the same time. So you have precedence, you have coincidence happen at the same time, and you have exclusion that say they do not happen at the same time. Once you have that, you have the patterns that I was talking about, and a simple pattern is the two things always happen at the same time. They are synchronous. And you can note here that I on purpose left more space between 1 and 2 than 2 and 3. This is the stretching effect I was talking about. In logical time, you can assume that you can always stretch the blocks. But these constraints here say that if you stretch this line, then you have to stretch the other line as well, because you require that they always occur at the same time. So if you stretch one, then you have to stretch the other one. For instance, low battery, I probably have a problem with battery very soon, but low battery, then you have to slow down your computer so that you save energy in your system. And then you plug the battery again, and then you go faster again, and you have full speed of your computer. So once you've done that, then you have other kind of coincidence relationship, like this one, which is subclock, which say they don't always occur at the same time, but if that one happens, C2 occurs, then it has to occur at the same time as C1, but in the meantime you can have other instance of C1, like this one or this one. This is a relationship we call subclocking. Once you start subclocking, then you have classical patterns that say, oh, maybe every third instant of C1, I have 2 instances of C2, and always the same thing. 1, not 1, 1. So this is a pattern of synchronization that you define between C1 and C2, and this pattern is reflected by this binary word here, which is infinite, but which is periodic. So you say that the first occurrence of C1, you don't want to care about that, so you ignore this occurrence. Then you have 1, 0, 1, meaning that this one you care about, and you have a synchronization. This one you don't care, and you skip it, and this one you care about it, and you have a synchronization. And so you have this periodic behavior, 1 on 1, and you replicate it infinitely often. This is the meaning of this filtering operator. You have something we call delay. Delay is something where you skip the first instance, so you take a delay at the beginning, and then you are synchronous all the time until this one stops. Then you still have 2 more tokens to play because you had 2 ahead at the beginning. So this is the operator for the delay. And then you have one which is periodic, and this one you probably know about that. Except that it's not a physical notion of periodicity, but a logical one. What you say is every third instant of C1, I have 1 instant of C2 with an offset of 1. So 1, 2, 3, 1, 2, 3, 1, 2, 3. And now if you fix the distance, the physical distance between these 2 occurrences, so you say between 2 and 3 I always have 10 milliseconds, then you go back to a classical notion of periodicity that you know all about. And so this is just a kind of a more general case of periodicity that people don't speak about, but that in most systems they do that. Even when people speak about physical time, I mean, if you go to microelectronics engineers, they have models, for example, they have languages like VHDL. VHDL is a language to design computers, to design processors, to design circuits. And in VHDL, you only speak about physical time. You have 10 milliseconds, you have 10 seconds, but actually, you don't care so much about the unit. You can stretch the time, and if you look inside the VHDL simulator, you are stretching the time by using something they call delta cycles. Delta cycle you can have as many as you want, and to run a simulation of 10 physical seconds it may take days. Usually when you run a simulation of a circuit it takes 2 days, and you only run for 10 seconds of what will actually happen in the system. So you have this notion of physical delay or delaying, stretching the time in any system, including the system that are physical languages. I insist on that because I may seem crazy speaking about logical time, but there was a company called ICTERI Technology. Her job was specifically to synthesize circuits, and all their mathematical model was based on this logical notion of time and of multiform logical time. So it's not just a crazy idea from a scholar somewhere. It's really something that is actually used in synchronous systems. You have heard of synchronous systems. They are all made on this assumption that you can say two things happen at the same time. So then you have plenty of operators. I showed you very simple one, but you can imagine more complex one. So this one is about intersection. Intersection is, you just imagine that every time, so you want to make the intersection between C1 and C2, and you know that, you know this relationship, then you can deduce that the intersection of C1 and C2 is just that clock. You have 3 instances here, because you have no coincidence relationship either between 4 and 3 and 5 and 3, then you don't have anything here. If you now you come back and you have a relation now there, then that will modify the way the intersection is built. Similarly, you can have union. Union again, here you know that you have 3 instances, but you don't know how they relate to these 3, 4, and 5 instances. You just know that you have 3 because you know that this one is not at the same time as this one, but you don't know how they position. So the purpose of that slide was mainly to say that the solution is not, you don't have a single solution. So the purpose of the tool we're building is to take these constraints and propose one valid solution for this system, and to explore all the solutions to say what are the best ones according to some criteria. And sometimes you don't have one single solution, so you have to explore all the possible solutions and pick the right one. This is what we call clock calculus, where you have to compute the clocks, meaning you have to compute all these relationships based on what you have at the beginning from the constraint system. So I have many of them. I won't enter too much into detail. This one is important. This one is precedent. You saw that yesterday. So this is a producer-consumer scheme. You produce, you consume, and you don't know when you will consume. So potentially you have plenty of resources, you need plenty of resources to do that. The way I do it, it seems that the communication FIFO between that and that can be simple, but actually the semantic of that say that you cannot compute the size of the communication media. And this is often what's happened in systems. People, they design mechanism and they don't think of what kind of property you have. So one thing we're trying to do is saying, if you say that, you will have problems. So you have to modify the design in a way that you will be able to compute the size of the communication first. And there are plenty of theoretical models that allow you to do that. And we try to use our language as base to introduce these theoretical models. So I don't have time to speak about those models, but those of you that know process networks CAN process have been designed specifically for this purpose. First, to do easy parallelization of code, and second, to guarantee functional determinism and measure the size of the communication buffer in a system. So this is just a syntax somehow to introduce all these notions that exist in this theoretical field. So usually you cannot live with unbounded systems, so we have a syntax to say it's not unbounded, be safe. I guarantee that I can do everything with a buffer of size 2. This is the meaning of that 2 here. This one is very useful for the braking system I was mentioning. When you brake, usually you apply pressure on the brakes. You have 2 brakes in the car, sometimes you have 4. But you apply the pressure on the 2 front wheels, for instance. But you never know if you apply the pressure on the left wheel or on the right wheel before. And depending what you do, you may have the car that slides a little bit on the right or on the left. So you have very complex computer systems in your car that try to adjust the behavior of the car depending on whether you press on the right wheel first or on the left wheel first. And you really have to have, you all know about ABS, but you have also other systems that are there just to guarantee that what happens in the car keep you safe. And this operator here has just say that I will put the pressure on left wheel, I will put the pressure on the right wheel. I want to know which of the wheel has got the pressure first. And you have another one that is called the sub, which is the opposite, which says which of the wheel receive the pressure last. And once you have the first one to receive the pressure and the last one, then you can impose constraints between them, saying, I want to be sure that every time I brake, the duration between the first wheel to receive the pressure and the last wheel to receive the pressure is not much than that much time. And this is classical in automotive industry. This is also classical in avionics industry. When you apply some things, you must think of a plane as very, very long things. So when you command the plane to do something, you want to be sure that every sensor or every activator in the plane receives the command within a bounded amount of time. And so you need operators like that to capture the time at which everyone receives information. Yeah. So this is the last part of my talk, which is supposed to give application of that. When I say application, it's still academic application, but it's academic application applied to some industry standards. So what we have here, we have a language that is was designed. The main architect of this language were people for Carnegie Mellon. It was intended at the beginning for automotive people, and the automotive people didn't want it. So they managed to sell it to people from Boeing. And after a while, it went across the Atlantic, and now Airbus is very keen of using that kind of models to design their system. So this is a language that is called AADL, Architecture Analysis Design Language, and this is a standard from the software engineering and automotive engineering, SAE, and it is actually used by Airbus engineers to design the system. And as I was saying, because it's an embedded system, what they care about is two things. First, the application, and you have a set of notations that look like a flow of things to do. When I design a plane, I want to sense some information, and then I want to process this information, and the result of that process goes to another process, that goes to another process, that eventually ends up in an actuator. And they thought UML was too messy for that, too big, and so they have designed their own languages where they focus on the key things that are important to them. One of them being the flow, the end-to-end flow, what happened between the sensor and the actuator of the system. I have a flow and I have a set of functions I want to execute. And they don't really care about what function it is. They just care that they have all these functions to do. And because it's an embedded system, they also want to design the platform, the execution platform. And so they have this notation to represent nodes. And in that case, they have 2 processor units, and they have a bus to do the communication. And then they have this binding arrows that say this thing, this process is allocated to that processor, and this process is allocated to that processor. So because we did the Marte profile with people from Thales, and Thales is working a lot with Airbus, then they wanted us to show the relationship between Marte and ADL. And so ADL is actually quite simple. Marte is very, very complex. So what we ended up is showing that in a specific annex, in a specific chapter of Marte, that we could capture all the key notion of ADL in Marte. And after that, Marte has been recognized as the notation to capture ADL specification. So ADL specification, there are specific tools, but if you want to capture ADL specification, then you can use Marte tool to do that. And what we did is we showed that CCSL was expressive enough to capture the main property of ADL and to compute relationships and to compute, to schedule application on the platform. So the main game here is that you have these functions and you put annotation on these functions, things like periodicity execution. So you say this process has to be executed every 10 Hz. And this process has to be executed every 50 Hz. This is the specification. And now you want to see whether you can allocate this function to the right execution units so that you still maintain some constraints. For instance, you want to maintain some maximum duration between the sensing and the actuation of something. So this is the main problem of ADL, schedulability analysis, as I was saying at the beginning. You have an application, you have annotation, time annotation, and you want to make sure that you can allocate the function on the execution platform. So there are a lot of fancy notations to say many things. I won't enter too much into details, but we show that all of these notation we can capture that using the language I showed you before, the CCSL language. So just to show you how that works, this is a simple application. I didn't like this one because this one it's more realistic in terms of what Airbus is doing. But this one is sequential. And sequential applications are not very interesting to me. And so we used variants. We asked questions to Airbus guy and they say, why do you do it sequential? He said, because nobody knows how to program something that is not sequential. So we asked them what you would like to have instead of the sequential process. And they came up with something like that, where you have functions that you know you want to compute in parallel, and at some point you still want to do the same kind of computation. Except that for now, they don't know how to do it. So they just assume everything is sequential. And so this is the same kind of application, except that you have 2 steps in parallel, and at some point they have to synchronize, and then you execute the third step. And this is FIFO. And in first approximation, we assume, so we put clocks on the inputs and the outputs, and then we put clocks also on the functions, so that we can control at what time you capture the inputs, what time the step 1 is executed, what time step 3 is executed, and what time the output is released. So you use the clock stereotype to do that. Once you've done that, then you can write a CCSL specification, and I wrote it by hand here, but we have tools to generate it automatically. And what you should see is that these things here, which is a data node in activity diagrams, and actually represents an unbounded FIFO. So at first you assume that the communication between this process goes through an unbounded FIFO here, and then one thing you want to know is whether you can schedule your system using bounded amount of memory. So first thing you assume unbounded memory, and then you will try to show that there is a schedule that uses a minimum or at least a bounded amount of memory to do the thing. One thing to bound is to use this kind of operator I talked about, sup, and you bound it with the, so you bound something, a relation between the inputs and the outputs, just saying that I don't want to use too much memory. So once you do that, we built a tool that we call time square. And one thing with OMG specification is that you have to have tools. So the profile has been implemented by most tool vendors, and if you take Rational Architect, or if you take Magic, or if you take Rhapsody tool, you will find the multi-annotation. But the annotation are not useful unless you have tools to process them. And so we built a tool that was integrated with some of the graphical editing tools, and that can use this annotation to produce analysis or schedules out of the specification. So this tool is called Time Square, and it's available here to try. And if you put this kind of specification inside, then it gives you something like that, which is a possible schedule of what's happening. So here you see the stretch time. These blue arrows represent the maximum flexibility you have, which say, because I have this arrow here, I can stretch, I can actually delay this execution here as long as it doesn't go in front of that one. And this one can be stretched also either way, either back or forth, as long as it doesn't go above this one. So you get to see the maximum parallelism available in your application with that kind of thing. And if you bound it, then you see that you're using much less resources, because this is the input, this is the input, this is the output. So this is the duration it takes between the input and the output. And here you see that between this input here and this output here, you have received many requests, 3 requests. So do you need a buffer large enough to store those requests before being able to compute the output? And this is not good. When you need too many requests at the same time, either you lose some of them, which happens all the time in Linux systems, or you need to enlarge your FIFO, and you need to know how to compute this value. And actually, we can show that with this specification, it's unbounded. So in a worst case, you need an infinite memory to compute this specification, which is not good. I mean, because you don't have infinite memory, and so at some point you will crash. So what we have also is we have this system where we take as element the task, and we put a clock on each task. That's something I showed you before. And then you want to put relationship between the tasks. So one relationship you can do, as I did at the beginning, you can show that this task is twice slower than this one. And then you can use the same operator. If you have a clock that you call millisecond, then that makes a link to the physical time that you know. So you need to say that there is a particular clock that is the physical time. And for instance, that represents the milliseconds. And then the instant of that particular clocks are spread by exactly 1 millisecond time. So now if you make relationships between that physical time clock and that logical time clock, then you connect your system, your your logical specification to the physical time. And one thing we try to say is that you should not start, usually engineers start by doing that, and then they are stuck. And they have infinite memory problems, and they don't know why, so they patch it and they make it sequential, and then it's kind of bad engineering practice. So what we say is you should start by this part, the logical part, and then at the end, when you show it works, then you can add the physical information. And if the physical information change, then you can see whether it's still valid or not. So here you have the same filter, except you have a weight of 10. So that means that this task executes every 10 milliseconds. So you have a 100 Hertz task, and because the other one is twice slower, then it's a 50 Hertz task. So at the very end, when you're done with your logical analysis, then you can add the physical information and see whether that still works. So I do what I did before on the application, then I add this information about the periodicity of tasks, and then I do allocation, saying that this step is allocated on this task, this step is allocated on this task, to this task, and the third step is also allocated to this task. And I do that using simple CCSL declaration. It's done automatically by the tool. And after that, you can also say that because these two steps are allocated to the same task, they cannot execute at the same time. So you have mutual exclusion here. Once you've done that, then you have a full simulation of your system, and you can guarantee that your application model will actually run on your execution platform. And this is really a key in this is called Y chart. Some of you that know that. Y chart, where you have an application and you have an execution platform and you bind them together, and usually you have to refine this part, the application part, until it's match the requirement imposed by the platform itself, and until you can actually put those numbers. I think I have theoretical issues now, but I'm not sure I want to go through all of them. So that was the application, saying that we took languages like ADL, Avionics Standards, and showed that our formal model is able to capture the main idea of this model. We did that also for automotive applications, where they have a language that is called AutoSAR. AutoSAR is a consortium that is made by German cars, and that has also a time model, TADL2, and we also showed that CCSL was adequate to capture most of the constraints they had in AutoSAR system. And we did that also for another language which we call IPExact, which is used in soft industry, in ESL design, to show that this language called IPExact has very bad property. It's supposed to allow reuse of IPs, but it doesn't have any information about the behavior of the IPs. So you just have typing system, and you put IPs, and because the type are correct, they just assume that it will work. If you want to do more than that, then you need to have more information. And what we propose is to use languages like CCSL abstraction that would give an abstraction of the IPs and allow the verification, validation that this IP would actually work together without just assuming that the type are correct. So we did that for a couple of industry standards. And but on an academic point of view, we also ask ourselves a set of questions. So very quickly, I think I have a bit more time, but I don't want to bother you with all these theoretical questions. So two kind of questions we're asking ourselves. First is about boundedness issues. We understood that for me it's very critical to be able to guarantee that you will not run out of resources. We had a talk saying that the resources were scarce. This is especially true in embedded systems. This is one of the main constraints of embedded systems, where you don't have lots of resources, you don't have much time, you don't have much memory, so you have to take care of them. And so one of the questions is, when you write specification, will you be able to satisfy it with the amount of resources you have, and in particular with the amount of memory you have? So that's the main question, boundless issues. Or can you guarantee that your specification is actually bounded? So we do analysis and we show that sometimes it's bounded, sometimes it's not. The other issues is what I call schedulability issues. And depending on what you do and what kind of allocation you do, you end up with specification like that. This is a very classical example, even if you don't understand it. Then you do the analysis and you end up with something like that, which is very, very bad. Those of you that can read it, you have a state machine, which is supposed to represent the state space of your application, and you have a kind of exchange between this guy and this guy, so some things goes well, except if you do that thing, you go here, and here you're dead. You don't have anything to do anymore. So this is about schedulability analysis. Do you have paths that leads to points where you cannot do anything anymore? And in that example, just replacing this simple equation by this simple other equation, then you create deadlock in your system and you're dead. So two main questions: safety analysis, do you have enough memory to do your things? Second main question, schedulability analysis. Considering your specification, are you sure that you can, that it's safe to run your system and you won't end up in a world where you don't have anything valid to do anymore? Okay, so yeah,
excuse me, Frederick, concern in flux. How many times do you need?
I'm not, but that's the fact. So I'm really done. The only thing is we want to have a more complex model, but I really think I'm done here. So if there are questions, I will be happy to answer, or if you feel that you have to think about that, you can come and see me. I'm still here until I think Friday. Thank you very much.
Put the question, please.
You are first. Really?
I have one question. You showed in one of the transparencies the scheduling, how to compute the schedule, given the different sequences. So my question or the comment is with respect to that aspect. Namely, when you want to compute a schedule, are you looking at a global time for scheduling? Or it is a distributed scheduling? I mean, that is something to be looked at, because when you say you are stretching,
yeah,
it seems to be you're looking at a global time. Am I right?
Not exactly. The thing is, we do it in two steps. The first step is we don't look at the global time. So the key point is we assume that you can stretch, and there is a whole area of research that is called latency and sensitive design that was done specifically for microelectronics. That is, you have to be sure that your logical specification is insensitive to latencies. That means you have things that happens, and then you have a logical connection, a causality between that thing that happened and that other thing that happens. You have to be sure that whether this thing takes 1 second or 1 hour, it doesn't change anything. And that's all the point of...
By 1 hour.
Sorry?
What do you mean by 1 hour?
I mean 1 physical hour to execute. And you have to be sure that whatever the time it takes, it doesn't change the functional behavior of your system. That doesn't mean you will meet your deadlines. That means that the functional determinism is preserved, and that's the main result from CAD networks, where you guarantee that whatever the latency, whatever the duration of these things, then you guarantee the functional determinism of your application. So at the first analysis, we take logical analysis of the specification, just considering the causalities between all things that happen in the system, and we show that these causalities are consistent and that there is a schedule that satisfies all these causalities. Now, of course, when on top of that you apply real-time constraints, then you guarantee determinism and maybe you lose the time determinism. I mean, you lose something. And that's in the second step where we use these constraints here, where you take into account physical time. So now you know you have a solution and logical specification. Does it still hold if you apply the real-time constraints? And that's where we consider real-time physical time in your system. But first, we want to do the logical analysis first, and then we consider physical time after that.
First of all, thank you for this interesting talk. It's a really complex problem. My group and we also have some experience in real-time system programming. Definitely it's spectacular. I have two questions. First question is, as far as you consider time, not atomic, really, you consider that as a complex system, complex feature. Maybe you need in your clock constraints language something like transaction mechanism. For example, one point begin, something to do, but if you are not happy with the result, you should be able to come back. My question is it maybe from concept necessary to put something from transaction or not? This first question.
That was exactly the meaning of the last slide, which I didn't show. This slide here, what I call the more advanced task model, was exactly that.
In your plan to make something of a transaction.
The thing is, we think we have the expressiveness to do a transaction-like mechanism, doing that, but that would flatten the system to 2 points, the point where you start, the point where you end, having a duration between that. And for now, we are able to do the analysis flattening the system, but then you lose some information because you lose the sense that this was the start of that thing. And so what we want to do is to be able to do the analysis
but you
keeping this relationship.
You don't use term transaction, yes?
This is a kind of transaction. This is a transaction where you have the start of the transaction, the finish of the transaction. This start-finish thing means transaction. This is the start of the transaction, this is the end of the transaction, and we don't consider for now the word transaction. So we put points, and we do the analysis with that point. But we plan to take into account transactions.
And second short question. You consider definitely multi-dimensional space for non-functional features. You have nice slide, but sorry, I did not have this number of slide.
Okay.
It means if you consider some multi-dimensional space for these features, yes, maybe you need to elaborate, you need to introduce some kind of matrix switching 2 points in this multi-dimensional space of non-functional. Why? Because, for example, you now your focus is time performance. Yes, for this purpose you develop your own model. But we know definitely that in any real-time application, besides performance, we need to have some appropriate level of reliability. It means I'm interested for two, let's say, reasons, for two factors: performance and reliability. That's why maybe it's interesting to have some kind of matrix between two states in multi-dimensional space of non-functional features in order to go in some trajectory and to get some, let's say, target point.
Yeah. So you're absolutely right. We don't address reliability issues now, but this is something important. And most of all, we don't pretend to address all the problem in real-time scheduling. So we just want to have a language that is expressive enough to capture the problem. And so what we think, and we try to show, is that these clocks, even if they remind people of physical time, they are there to capture the multi-dimensions that you have. So on one of my slides, I showed that those slides could be could capture rotation degree. They could capture power consumption. So we have really example where we have clocks for time, clocks for power, clocks for rotation angles. Now for reliability, I'm not really sure what to say, but we really think that these clocks are there to capture all the dimensions and all the kind of relationship we have between these dimensions.
Thank you very much. Thank you.
I think I have only a short question. The question is, what state of ripeness has this Marty tool achieved now in version 2? Do you think it's possible to give it to a typical electrical engineer and he can do something with it? Or when do you expect to reach this state?
No, I think it's not possible. Electrical engineering may be the worst example because in my experience, semiconductor industry and electrical engineers have been very reluctant to use something else than what they've been using before. So I was surprised to see the talk before mine, because when you go to Philips or you go to Texas Instruments and you tell them about that, they are still writing programs in basic C or in assembly language. So anytime you speak about something more abstract than C, they look at you with big eyes and say, well, what are you talking about? And they have been defining this language for IP-exact, which looks very close to what I'm saying. And it's very, very, very difficult for the industry partner to have the engineer accept that they have to change the level of abstraction. So for now, it's not, I mean, our tool is just a toy tool, an academic tool. IBM has invested a lot of money to have tools around Marty, but even though, I mean, I'm not sure industry and particularly electrical engineers are ready to accept those tools. I mean, really, we are working with Synopsys, we are working with Texas Instruments, we are working with Philips, and there are research departments that want that kind of idea to be pushed. But as soon as you go to the production line, production engineers, they say, what is that? I still want to do my code in C and I don't want to hear about any kind of this thing. So, no, it's not ready, and I don't know when we can expect to be ready.
Have somebody a question, please?
What do you do? It's happily runtime programming, mistake, or unregular regular errors. What do you do? Что делаем, когда возникают ошибки в runtime? Что они делают?
How do you handle error in runtime program?
We don't handle them. What we do is we propose a model, an abstraction, to capture the requirements, to analyze the requirements, and to explain to the engineer what he has done. And once he has done that, and he can see that he has a problem, then he has to change the specification. So we just propose to analyze the system, and if there is a bug, then we show the bug, and that's not our part, no job to fix the bug. So the engineer has to find another specification that match its need. And yeah.
Well, beginning from beginning.
Yeah, not necessarily from the beginning, but he has to think and he has to see what was wrong, and he has to change, and maybe he has to go back to the very beginning. Hopefully we hope that we help him to make abstraction layer, so he won't have to go back to right from the beginning, but just to the previous abstraction layer. But this is engineering, so yeah, he has to engineer.
Thank you. Thank you, President.
Ouais.
Today tutorial is closed.